Welcome again to this NPTEL course on storage systems. In the previous class, we were looking at aspects relating to virtual synchrony, and we were trying to figure out how to order failure events with respect to other events in the system. Now, I briefly started looking at ordering semantics with respect to messages last time. So basically there are issues regarding how to order failure events with respect to messages and across messages themselves. There are two aspects. So we covered the first part of it in the virtual synchrony model. Now we will take a look at the ordering of messages amongst themselves when they are going to be delivered. So I think I went through a few of them last time, when there are either no ordering semantics at all, or there could be FIFO semantics, in which the process either broadcasts or multicasts M before M prime, no correct process delivers M prime before M. So basically it is clear that the process is doing both of them, M and M prime. Therefore, in every process that survives, okay, it should not be the case that M prime is delivered before M. And this will take care of obvious problems that we have seen before. I think we mentioned something about in an email system, you will find that a response to a message comes earlier than the message itself. Okay, that's kind of stuff you want to avoid. Or in the case of the cricket scores, you essentially guarantee that if it is FIFO, you are more or less saying that the scores increase monotonically rather than go up and come down. Those things are avoided with FIFO. What about for causal? If broadcast or a multicast of M precedes M prime, no correct process delivers M prime before M. Now, this notion of precedence, I think last time we mentioned that there is a way to order events in a distributed system that is due to Lamport. And basically, it's we went through it a bit last time. Basically, all it says is that if, for example, a process executes E and F in that order, then if E is before F, then E precedes F, either that, or we are talking about messages in a system. So if E is the broadcast or multicast of some message M, and we look at the delivery of M at some other process, okay, then we can say that E is before F, E precedes F, because E is because E has been sent earlier, therefore it can be delivered, okay, obvious reason why E has to be before F. Or there is a transitive closure where we are saying that E is before H and H is before F, therefore you can say E is before F, okay. So basically if it is causal, in case if cast of M precedes M prime, then you want to make sure that no correct process delivers M prime before M, okay. With respect to total, basically here what we are trying to do is we want to order all the processes somehow. So what shall I say? If at a correct process P, M delivered before M prime, then M will be delivered before M prime at all destinations they have in common, okay. So if M is delivered before M prime at a process P, then it should be at all destinations, okay. M should be delivered before M prime, okay. This is the total order. It is a very strict and probably sometimes unnecessary restriction, but this is one model, okay. So let us take a look at an example. You see there is a message M0, there is a message M1, there is a message M2. Now, M0 does a multicast to A and B, and you notice that the message M0 comes to A at this point in time, and then B in turn does a multicast to C and D. Now, in some sense you can say that this event as seen from A is later than this one. Now, the thing is, this may be causally related to A or may not be. For example, this could be something and this completely independent, but our distributed system, not having this application semantics or higher level knowledge, has no way of finding out whether this is actually independent of this. All we can say is that as a person standing at A, we know that this happens later than A. Okay. So, a safe assumption is that this is somehow connected with this. It may not be true in principle in all cases, but it is a safe assumption. It is a conservative assumption. So, what we want to ensure is that if you look at M1, you want to ensure that the deliveries of C and D should be causally ordered with respect to the deliveries of A and B. Okay. For example, here you notice that A followed by this, therefore, C should be definitely later than A and D should be definitely later than A. If there is a system which does not guarantee this, then they are not causally related. Okay. There is something else M2 which is has no connection with M0, because notice that the only way I can say that M0 is causal, may be causally related to M1, sorry, M1 is causally related to M0 is because there is one common place A where I can see that this one is definitely earlier than this. If there is no such thing, then I can't really figure out what is going on. For example, this M2 goes to C and B, right, and there is no way in which I can say that. For example, here I see this is before this, here I can say that I can't really order this with respect to what is happening at A. And since the event happened here for sending it out, I can't really put M2 in correspondence with respect to whether it is before or after with respect to M0. Okay. Now, if I am thinking about total order, you look at B. Suppose my timeline is like this, M2 suppose has been delivered at B before M0 at B. Suppose I extend this particular message multicast to C also, okay. Then if M0 is also delivered to C, then should be later than M2, precisely because in this case it turns out that M2 was delivered before M0. Okay. Here you can say M2 has come before M0 at B. Therefore, if M0 happens to be also, let us say, multicasted to C, it should be later than that of M2, because M2 has come is before M0 at B. Okay. So, in a sense it has to be a global ordering. Okay. Now, in all these cases also, this ordering can also be let us say divided into two types, whether it is weak or strong, and it corresponds to whether things are dynamically uniform or not. As mentioned before, in dynamic uniform, you look at those processes, okay, which may be involved in it, but they die in between. Okay. So, we are saying that we want to guarantee those things with respect to those processes also, then it is dynamically uniform. If you are only talking about guaranteeing this with respect to only surviving processes, then that will be a weaker model or a non-dynamically uniform model. Now, when we talk about this precedence relationship, there is a way to order events in the system, and as mentioned, Lamport has defined it, and the formal notation comes from the notion of what is called logical clocks. And basically what we do is we associate a counter with each process and message in system. Let us say that at process P there is a logical time P, okay. It is a counter corresponding to that, and LTM is the logical time of message M. Suppose there is a new event. What can be the new event? It could be because the process P got a message, or it is doing something else, okay. Suppose it got a message, then what you do is you look at the message and see its timestamp, logical timestamp. So, because it just received a message, and if it so turns out my current notion of time is smaller than the notion of the time as seen by the message that I just received, then I tell myself anything that I do in the future has to be later than the message that I got. Therefore, it has to be my current notion of current time is going to be the most recent event, that of this message plus 1. Okay, that is what it is. Basically, I am updating my notion of clock. Similarly, if it so happens that I have done many more other things after a particular message has been received, I just have to increment my own time clock by 1. Okay. Here I put greater than equal to, it is just a technical thing, because simultaneity in a distributed system is essentially impossible. Okay. So, but in case it happens, you can still do this. Okay. So, if it is not because of a message, it is because any other event, I can also increment my clock. Okay. So, this is how I keep track of the time events in that system, and every event has got a counter, every event has a number which basically is the current logical time, and then in every new event I have to do something about incrementing that clock. So, it is basically a logical clock. Okay. Now, this kind of system works well if you have, let us say, number of processes that keep on changing with time. It is dynamic. The number of processes in the system is dynamic. So, it is a very general model, but it turns out that there is a more accurate clocks possible with static number of processes. It is called a vector clock. And if you are looking at something like causal models, these vector clocks are quite useful. That is why, for example, many implementations of causal ordering use vector clocks, because by definition in a group communication system you are going to be managing membership. Since you are managing membership, you exactly know how many processes are there during for that epoch before the view changes. Therefore, you can assume that between failure events definitely there has to be a fixed number of processes. Therefore, you can use a more accurate clock, the vector clock. Okay. We will look at the vector clock. What is a vector clock? Is a vector of counters, one per process and set. Basically, if there is an event E, what a vector time corresponding event, what it is basically is, for each process in vector, it essentially tells me how many events occurred in that process causally prior to when E occurred. For example, suppose there is a message M and I say it is 4, 5, 6. What does it mean? That means that there is the message M is, let us say, has that it has been sent, okay, and basically and has been received at this process P. That means that 4 events happened causally prior to sending of M a process P, 5 at Q and 6 at R. Essentially, you have a fairly detailed information about what all happened at each place, each of the nodes PQR. But if you look at the logical one, it all gets put into one counter. Okay, so you don't have that discrimination. So, I can essentially make finer distinctions with a vector clock than I can do with a logical clock. Okay. So, for example, I can know, for example, that for example, the number of events causally preceding some event at my place has not changed, whereas if in a logical clock it will be a different number because other events, and I can't figure it out, whereas here I can figure it out. Okay. So, suppose I have the notation VTP and VTM, these are the vector times associated with process P and M, the process P and message M. Okay. I also have another notation VT of P. As I mentioned, it is one per process in set. VT of P means it is entry in the vector corresponding to process P. Okay. So, this bracket thing gives you the entry corresponding to process P, whereas these are different vector clocks. Okay. Vector times, sorry, these are different two vector times. Okay. So, each of them will have some vector corresponding to that fixed set of processes. Now, how do I update a vector clock? Suppose I am at process P, my vector time is this VTP. I am going to do some event right now. I want to label that particular event with some vector time. What do I do? Because I am at process P, I just increment the corresponding entry for process P. I say VT of P equal to VT of P plus 1. Okay. Whereas, if I get a message from somewhere else, okay, I basically say VT of P equal to max of VT of P computer, because it may be later than where I am right now. So, I am at a particular point, I am not doing anything right now, and I get a message from somewhere else. So, I have to assign a particular time for the event that the message has been received by me, delivered to me. That means, it has to be connected with either the most recent time I have or the most recent time as reported by the message itself, but what is incoming message. And since it is a vector, you have to do a entry by entry max, that is what you have to do. Okay, because these are vectors, so max is basically there are so many entries, a fixed set of entries, and you have to do a max of each one of them. Okay. So, these vector clocks give you lot more precision in terms of exactly the kind of things that are going on in the system. Again, just to remind you, basically if you look at a vector time, it basically says for each process in the vector, how many events occurred in that process causally prior to when E occurred. So, that gives you fairly good view about what is going on in the system. Okay. And you can use that to determine which is before, which is after. Okay. So, again, if you are designing the causally ordered thing, you have to do these vector clocks. And then because anyway, as I mentioned, in a group communication system, you know how many processes there. So, therefore, vector clocks are definitely feasible. And then you can figure out what things are let us say causally ordered, and then when you do the delivery, you look at the times the vector clocks and decide whether to do it or not. Okay. If it is causally, or depending on the vector clocks, you can figure out whether it is which order it has come in, and then do the appropriate delivery. So, now the important thing to notice is that there are a lot of orthogonal choices in your design of this kind of systems, messaging systems. For example, the atomicity, okay, the failure atomicity, for example, okay, does not specify delivery order, and also you want to ensure that the delivery order, for example, could be FIFO, causal or total. Okay. It can be uniform or not uniform. Basically, you are deciding to say whether some whether you are concerned about processes that fail or not, basically about correct processes or not correct processes. So, various possibilities. It can even be timed, but as I mentioned earlier, synchronization is very difficult. but it's possible that you can design protocols with timeouts into account. Basically, you have some kind of timeouts, and then you can decide whether a particular multicast or broadcast has to be timed out because it's not received in particular amount of time. Okay. So, various choices are there, and different designers have played around with various aspects of this. Okay. And each one of them has certain difficulties. For example, dynamically uniform is far more difficult. Similarly, causal requires you to keep track of vector timestamps. That's more difficult than, for example, if you don't have any delivery order of specified, etc. Okay. So, this also requires some kind of synchronization. So, there are various levels of difficulty in all these models. Now, let me just mention that this causal model actually can be sometimes misleading. So, one has to be careful. You have to see exactly what its capabilities are. Okay. For example, consider a replicated database, and you have 2 copies of bank account on 2 sites. Now, it is possible that I have multiple operations going on. What is the first one doing? First one says deposits 20 units of currency. So, what is the equivalent of that? I have to multicast, add 20 to x. But so, this one user is doing this, but bank independently at some fixed point in time it can add interest every so often, and it says multicast add 10% to x. Notice that these 2 things are not causally related. The fact that I am depositing 20 is not connected with bank adding interest, right. But what is our big problem? The problem is depending on when I do this, right, I will get different results. For example, if I do add 10% x before I do this, I will get one result. If I do this first followed by 10%, I get a different result, right. So, these things are not causal related, but if you do it in different orders, you get different results. So, what is the understanding that you have to have? It is not specified by this causal model, because this is an application level understanding. The system has not given us enough information to decide what is to be done. So, it can happen in any order, so and you can't guarantee it anything. Okay. There has been a big controversy in these virtual synchrony models and those people working at application levels. As I mentioned, this whole area is full of controversies with respect to mathematical models, with respect to whether this virtual synchrony should be done at which level, should be done at the application level, should be done at the system level, etc. Okay. So, depending on all these things, you have different results. If you do it at system level, oftentimes you do not have application level insight. So, you may not be able to do anything. You might think it is not causal related, right, and you go ahead and do it, and you might get different results depending on which way it actually happens. Okay. The other issues similar to this, if you take a look at let us say that you have 2 entities P and Q. P is publishing certain values, it is computing. Okay. Basically, it is a publish subscribe paradigm. So, P is publishing these various values, and Q is picking up these values and it is computing some value. Okay. Now, because Q is receiving, you can actually go with a causal model, because once x0 has been published, definitely Q will get it, and because there is a message between P and Q, therefore, this will be causally connected, and therefore, you can guarantee that f of x0 is basically received after x of 0, that you can guarantee. But our problem is that you may not be able to figure out which one is which. See this, you may think that x0, x1, we have, for example, I want to operate on f of x0, but it may be that I can actually take x1 and compute and think that it is connected with the first one, whereas actually it is connected with the second one. Okay. So, so the thing is, there is a correspondence between the values that have been published which are coming on a stream and what I do with it, okay, they might be not causally connected. Okay. So, if you want to do that, you need to have additional information which says that this is the first value, this is the second value, etc. Okay. The causal ordering does not itself give you that. Again, this is related to the fact that we do not have application level insight into what is going on, and all I can do is I see values and I am doing f of something. Okay. And so, these protocols have to be carefully constructed so that this kind of confusions do not occur, and the only problem is at system level you do not have this kind of application level information. So, you really may not be able to do much. So, if you are concerned about those semantics which are dependent on such things, you have to take control at higher levels. It can't be done at lower levels. Okay. So with that, I want to start moving to a slightly different topic. Okay. So, we were looking at how to order events, and we were talking about how things can fail at the messaging level. I want to start thinking about what happens in case I do it at the storage level. Okay. We previously looked at NFS model, and because of the way it does caching, it was not going to be completely consistent. So, now let us take an example of a different type of file system, okay, the co-distributed file system that tries to be giving you good semantics as far as possible close to Unix semantics, POSIX semantics. As I mentioned, the clustering kind of file systems are basically these essentially the same as the distributed file systems which give you POSIX semantics. Now, let us see how this particular design was attempted, exactly what they tried to do, what kind of ordering that they wanted to put in, and how this, if you are thinking in terms of this virtual synchrony models, how they could actually be used here, okay, and why storage itself adds some other types of issues into the picture. Okay. So, we will try to look into some of these things. So, what is a co-distributed file system? It has got replication. So, there are many servers and even disks are replicated, servers are replicated. It has got caching as an important part of its design, but it wants to guarantee single copy equivalent. Now, this is different from NFS, because NFS has a slightly looser notion, therefore, it can't really guarantee the single copy equivalence. Okay. Other thing, it has got global naming. Again, this differs from NFS. Essentially, it has got a single system view. You will notice that in NFS, depending on where you mount the file system, you get different names for the same thing. Okay. Whereas here, you want to have a single system view. Okay. So, that global naming also is an important aspect of this particular system. Again, the reason why this is important is that if you are writing applications, you look for a particular file in the application and it has been mounted somewhere else, then the application will fail. Whereas, if you have a global naming, then it does not matter, it will always be at the same place. Okay. So, it is a slightly easier thing to work with when you have global naming, okay, which is not there in NFS. They also want to look into distributed security. Okay. Now, we will not spend much time on this part of it here. Okay. So, what did one of the most important things that did was what is called coherent write back caches for both files and directories through ordered write behind. So, again this is where the ordering comes in. So, what is write behind? It is basically something which is returned back after a fixed amount of time. Okay. I think as I mentioned earlier, in many file systems you have various models. You have what is called synchronous models, where when you write it, the application waits till the write has been committed. Only when it comes back and says it is done, it will proceed. That is the synchronous model, and it is quite slow, because you are actually going to be suffering disk latency, which is going to be considerable compared to what CPUs and memories can work, the speed at which they can work at. This other model, asynchronous model, where it's a slightly more relaxed model. What you do is you go to the storage system and say, please store it for me, but knowing fully well that it's going to take a long time, I don't want to wait for the completion. All I am guaranteed is that the request has been queued, but I am hoping that I am actually an optimist. I am just basically saying it will get done sometime. Okay, that's basically what is the model of asynchronous thing. I take the trouble to queue it, but I will not wait for it to complete. I just go back and do something else. That is asynchronous model. Then there is another one called delayed writes, which is basically the write behind. Okay, delayed writes is basically I don't even queue to the disk. I leave it in memory, and I hope that somehow someone or either a system or because some other reasons, all the stuff which I have written and made dirty in the memory, it actually gets written back to memory in some fashion. Okay, I am just hoping for other parties to flush it to disk. Okay, so basically this is also called write behind. Okay, now what is the issue with write behind? The write behind essentially, if it is not ordered, then something which got dirtied much later can get flushed to disk, and then you can suffer a crash, and then the previous write which never made it to disk may not be there. In some sense, you have there is an inconsistent version of the system, of the file in the system. Okay. So I want to do ordering of, if I can do the ordering of write behind, then I can do something reasonable. That is one thing which this particular echo file system attempts to do. Okay. So again, this particular system has got a large caches, then these things are supposed to be completely transparent except on faults and crashes. That is, you won't notice that there is a cache at all in the system except when there is a problem. Okay. And as I mentioned earlier, this particular design tries to avoid certain drawbacks such as incoherent caches like NFS. NFS also does some close on sync, that is, whenever a file is closed, it flushes to disk. Okay, but it does not do the same thing with respect to directories. Okay, we also looked at this open file problem. If it is deleted, I think we mentioned that NFS has a certain workaround for this problem, but it is not complete in all aspects. Okay, so there are other issues in NFS which has to be handled, and so this particular model tries to do this one. Let us see what they are doing. Okay. So again, to be able to do this, they have a particular model. Basically, file system data is changed only by write, that is logically done at distinct point in time. That means even if it is done over a period of time, you can logically see it as being done at a precisely one single point in time. Okay. So essentially similar to what we discussed in the case of serializability in databases, or when it comes to the closely synchronous model for message delivery. Again, this also tries to do something similar. Okay. So, and for the same reason, if a fault occurs, this causes certain writes to be discarded. Again, this is done at a distinct point in time. Okay. So that you can reason about it without too much trouble. Okay. So again, when there is a network partition, you either block or you are told that there is a timeout, because similar to NFS hard and soft models. So various read operations in system, and there are write operations in system. Okay. So this is roughly the model of echo, and we would like to exactly start modeling aspects relating to the ordering of writes. Okay. So if you want to keep the file system consistent, then if you are going to drop some writes, because as I mentioned, because of faults, some writes can be discarded because they are sitting in memory still. okay, and we are saying that it is undone at a distinct point in time, and we do not want any inconsistent results. Basically, in some sense, it should look as though time is always progressing in the forward direction. It should not look as though time has moved backward for some operations, that is, some things are undone but something has moved forward. Okay. Those kind of inconsistency should not happen. Okay. So, that is why I need to do ordering and ensure that a consistent way of flushing writes to stable storage has to happen. Okay. For example, this is some of the conditions that we have to satisfy. Write requested by one client and observed by another. Okay. So, basically, if that is the case, it is already been observed by another. That means that it has to be stable. Okay. The minute I request write to be done and it has been seen by somebody else. Okay. Now, I can't just leave it in the memory, and if there is a power failure, I can just drop it, because it has been observed by somebody else. Observed because this party who is not me has actually seen it. Therefore, that means that it should definitely be stable, so that if somebody else looks for it, it is also available. Okay. So, this is one critical thing. Writes on same object should be stable in logical order. Okay. So, if it is I am writing to the same object, they should also become stable in same order. Again, this also is related to what SCSI also requires. So, SCSI also requires that if I send multiple writes in some order, they should get committed in the disk in the same order. Okay. That also is there. Okay. The only thing that they try to relax with respect to overwrites. Overwrites, what are overwrites? Basically, I am not increasing the size of the file. So, there is a file, for example, 8 megabytes, and I am always writing inside that 8 megabytes. Okay, I am not really extending the 8 megabytes. So, if there are multiple writes, some at, for example, 1 megabyte, some at 4 megabytes, some at 512 kilobyte offset of some multiple blocks, then it can be reordered as an optimization. Okay. So, this is one thing they are willing to relax. Okay. So, in this particular file system, they decided that this is not something critical. The reason being that you do not want to relax it in other contexts across multiple files, is because you might use the files as a way to know when to order events in the system, whereas doing it on the same file is oftentimes not a common idiom. It is not done that much. That is why it is not. So, they have decided that that can be relaxed. Okay. And that is the reason why they have this particular notion that overwrite is basically failure atomic if only one block is modified. Again, why is this the case? Because notice that if you want to do overwrites, it is basically a read, modify, write. You have to read it, update it, and then flush it back to disk. Okay. If you are going to have this reordering as an optimization, then you can't really guarantee failure atomicity, which is not possible. That is why these two things are connected. Okay. Now, the other thing that they have in mind is some ordering operations. fsync is quite well known. It basically is a command that can be given at application level to synchronize the file contents which are sitting in memory. It can be flushed to disk. That is fsync. And so, it is possible to do it on directories and files. So that when it becomes stable means it is sitting on persistent storage like disk. In addition to this, there is something called f order, because notice that fsync is only on particular directory or a file at a time. But suppose I am interested in constraining the order of multiple files or multiple directories. I want to specify the order in which some particular operation takes place on certain files. Then f order can be used, and this is something which is not there in POSIX. fsync is there in POSIX, but f order is something which is there so that you can essentially satisfy these conditions. Okay, various design aspects about coherent write back cache, etc. For these things you need F order. So this is something, it's a new thing, it's not part of POSIX. So other thing that is different about an fsync and ftort is, fsync basically you wait till it is committed to disk. That means it's a synchronous operation, and the only reason why it's called fsync is because it's synchronous. You are sure that at the end of it you have done it. Okay. Whereas F order, it constrains ordering of write, but it returns immediately. Okay, unlike fsync. Okay, basically this is just telling you what the order should be. You are intimating to the file system that please make this, please flush in this order. Okay, it's not a, you are not waiting for it to do it, you are just telling it whatever you do, keep track of this, and in the future if you are going to flush it, please make sure this happens. And it has to be, in spite of whatever crashes, whatever has happened, you better follow this order. That's all I am telling. I am instructing the file system to do it. For example, suppose I say F order F1, F2, etc. Then basically this F1, F2, etc. they are logically performed before any operations after. Okay, this have to be done before any operation that come after it. Okay. Now the reason why this is important is that consider, for example, a rename operation. Okay, rename is a fairly complex operation for a file system to handle, because what are we doing when rename? This is the source and this is the target, and basically what we are saying is that I am going to graft this tree at this place. That means it is a whole tree is getting moved from one place to another place. Okay, that means we are going to modify the directory A, the directory B, A/F, B/F. And so basically there are, actually there is more than that, but for simplicity we can say it is equivalent to 4 operations. And if you are operating at 4 different places on the disk, you have to ensure some model by which, in spite of failures, it is doing something reasonable. Okay, the semantics is slightly complicated. Okay, either you can do the following: you can say that I keep track of the way it is happening. In case I crash, when I come back up again, I remember where exactly I was and I redo the rest of the thing that didn't complete. Okay, that's one model which is typically followed by file systems. Or I can say that I do some things and then when the machine crashes, I undo whatever I had done so far. Okay. Now since file systems usually do not have extremely long running transactions, it is simpler to go with redo models. Okay. So for redoing, I need to have some information about the way I had to flush this into disks, and that is what F order can be used as a way to tell it which way it has to be done. Okay. So and this can be arbitrarily complicated because this tree etc. can be arbitrarily complex. Okay. So the standard way it can be done is through transactional models, and most generating file systems do this kind of operations using some log, and the idea is instead of using a log, can I do F order? Okay. The F order also can constrain the order in which something has to be flushed. And some of these things are also used in some commercial file systems similar to F order. For example, if you look at the BSD file system, fast file system, they use equivalent of F order. Okay. There is a particular scheme in that system by which all the buffers which are dirty, you keep track of the dependencies, and then you, when you are flushing it, you look at the dependencies and then you actually flush them in that particular order. Okay. So in a sense, BSD file system has some notion of order, but it is not available at the application level, because notice that fsync is available at application level and so is F order. Whereas what BSD is doing is it's done at the kernel level. It's not really, it's not available at the user level as a way to constrain things. That means that they have to do some specific things on top of this. So it is basically a slightly less elegant solution than having something like F order. So let's look at further details. So in this echo model, you need to have two things. One is data dependency and one is the ordering in which stable writes are going on. Again, what is a stable write? A stable write is one which is persistent in disk. It is persistent. It means it cannot be, you cannot go back. It has been, once it has been equivalent of committing to disk. Okay. And both these things are required, because basically what is happening is that there is something in memory, something in disk, and you want to carry the contents of the memory to disk in a particular sensible order. Okay. So, that is why I am keeping track of data dependencies. I am also keeping track of how things have been ordered in the disk. It is a partial order, because sometimes there is no ordering required, it can go in any order, but sometimes I require a particular order. Okay. That is why there are two relationships, and then let us see exactly what they are doing. Okay. So, it turns out this partial order for stable writes is a subset of data dependencies. Okay. It has to be, because if it is not dependent, then you can do it in any order. So, if it has to be ordered in a particular way, it is because there is a reason why certain things have to go in a particular order. That is why you are going to have the stable writes, they are ordered in one way, and the data dependencies are going to be a superset of this particular set of things that have to be done. Okay. And these two things are transitive. Okay. Now, let us look at some of the conditions they have imposed. If O1 data dependent O2, okay. Okay. So, what does it mean? It means that O2 is dependent on O1. So, O1 is first and O2 is later. O1 is a write and O1 O2 have an operand in common. O1 performed logical before O2. O1 not discarded and O2 performed. Okay. That means that you take the distributed system, and if somebody says O2 has been performed, then O1 cannot be discarded. That is, even if it is sitting in memory, whatever it is, you have to somehow flush in particular order in such a way that O1 in no circumstances will ever be discarded the minute you say O2 is performed. Okay. Because O1 is prior to O2 and there is the data dependencies there. Okay. If O1, there is a partial order with respect to O1 and O2. Okay. What is this saying? If this is the case, only if O1 is let us say O2 depends on O1, O1 and O2 are writes, but not overwrites. Okay. So, what are we saying here? We are saying that if you are going to do something, because these two are writes, right, I am trying to ensure that if O1 goes to disk, okay, then O2 could be discarded. We are not really saying O2 should be. The fact that O1 has gone to disk does not mean that O2 has to also be gone to disk, does not matter. Okay. This one, all it is saying is that there is a order in which these two have to become stable. That is all it is saying. They already have a connection with respect to the dependence, but I am also telling it how it should happen in case I flush to disk. Okay. What about this? If O1 followed by this arrow O2, O1 discarded implies O2 discarded. So, this is the opposite of this. Okay. Basically, in case, what did I say? Is basically O1 should be, if in case I am going to make things stable, then if it turns out that O1 has been discarded, that means O2 should also be discarded. This is another condition. Okay. Now, if O1 is if O2 is dependent on O1 and O1 and O2 on different clients, O1 stable when O2 performed. Okay. So, its operation O2 is done on a different client, I also have to make sure the O1 is stable, so that other parties also can notice it. Okay. So, if it is not stable, then I cannot guarantee if O2 is performed that O1 can actually crash, right? The operation, the node on which O1 was done can crash, and then there is no way to do it. That is where O1 has to be stable. Okay. Now, if O1 in terms of ordering for stable writes, okay, if O1 has to be made stable before O2, then if O2 is stable, that means O1 has to be stable. Okay. And if F sync of F is successful, F is stable. Okay. Now, so you have various rules of this kind, which basically tell you how you should structure your flushing of disks. Okay. There is also, as I mentioned earlier, there is also F order also is there. Okay. And this also will tell you if it is logically performed, that means if it has to be made stable, in which order it has to be done. Okay. Now, you can use both F order and F sync, and F sync will be a heavy handed approach. If your file system is able to use F order, if it has got that notion, then the application level ordering through F order can be used by the file system to decide which order should flush it, and then while keeping all these things in mind. Okay. So, the basic condition is the following, is that if you have a partial order for stable writes, you have to ensure that it happens in that particular order. Okay. The data dependence basically just tells you what is the let us say what is dependency of one operation or other. It does not say anything about what should happen on failures, it does not say anything, whereas this one says what should be done with respect to the flushing if there are failures. Okay. So, that is why we need these two notions, and what we are doing here and all this when we are describing all these things is to take care of the situation where you will only have the writes in the way this particular order has specified. Okay. You want to make sure that they all get flushed to disk in a particular order. Okay. And using this, you can come up with models for things like the following. Like for example, when we talk about rename etc., we can actually sit and work out exactly what the application or the, let us say the application, high level application has to specify, and that can be used to ensure that this really happens. Unfortunately, this F order is not really part of the current API in POSIX. So, what you have to do is to do F sync as a way to order things. So, this turns out to be far more let us say costly. In future, when we have things like flash storage and other kinds of fast storage, it probably I think there will be a lot more concurrent activity in the storage system. I think at that time probably people will probably start designing APIs which correspond to things like F order, and that might actually make a lot more parallelism possible. Currently, the reason why it is not done is the number of disks is quite small typically, and the need for parallelism across multiple disks is not that very high. It is there in big databases and some other systems, but in most systems the number of disks are rather small. Therefore, you do not have this particular need to figure out how to have some partial orders, so that many things can be flushed to disk in relaxed orders, and only those things that need to be ordered in a particular way can be specified and then flushed to in that particular order. Okay. So, I think with storage class memories or etc., what will happen is that there is a lot more let us say subdivisions in the storage system which can be run in parallel, and then I think all these things will also, I think I suspect that this part of the storage system will get essentially new APIs, so that this can be done effectively. Okay. I think I will continue next class based on this particular model. Okay. I will show examples of how rename etc. can be done with this particular set of operations.